Today I'm going to talk about holography, scale invariance, and inflation based on some work with Daniel and Tom Hartman that we hope to finish soon. Okay, so this is not a slide that's really needed for this audience, but of course inflation is a broad set of ideas, and there's a lot of questions that we'd like to answer about it that we hope to address with data. So for example, we'd like to know, is inflation a strongly or weakly coupled phenomena? How many degrees of freedom were involved? What kind of symmetries played a role in the mechanism? Perhaps more ambitiously, things like, can we show definitively that quantum mechanics is the origin of fluctuations in the universe? The question that I'll be interested in particular here is, are there consistency tests of inflation itself? So there's been sort of partial success of varying levels depending on the topic. So the squeeze limit of correlation functions as being a test of the number of degrees of freedom is a pretty robust example where we have good understanding. Same with B modes and the scale of inflation in the field range. Non-Gaussianity we know is related to things like interactions and degrees of freedom, although there's not sort of a one-to-one map. But then there's the cases like, could we find some kind of Bell inequality, something that you could measure that would definitively test quantum mechanics? That would be nice. And the one that I'm going to be interested in here is there's some kind of sum rules for inflationary parameters, ways to directly relate the values of things we measure to the UV physics that it comes from. And to make progress on some, especially these last two, we're just going to require new tools or insights beyond what we have right now. Okay, so this is sort of one of the motivations for the talk, is these looking for something like a sum rule. So I'll give a basic example that we heard many times last week, which is to take, so I take a scalar, so this is the simplest example. I take a massless scalar field and I add a quartic coupling with 4 derivatives. And you can use a dispersion relation after computing the 2-to-2 amplitude in this theory. And you can directly relate this 4-derivative coupling, lambda, to the integral over the total cross-section of the theory. So this tells you this is a direct relation between some low energy parameter you could measure and what's happening in the theory at much higher energies. It also, interestingly, enforces positivity. So this coupling a priori could have taken either sign, and you show that it definitely has positive sign. And perhaps more surprisingly again is that when this value of this one coupling is 0, it tells you that all the couplings in the theory are also 0. So you fully determine a theory by knowing the value of one coupling. So a natural question, is there some inflationary analog of this type of sum rule? So a natural guess would be something of this form in terms of the speed of sound of the inflationary fluctuations, the scalar fluctuations. So here I've written as 1 minus CS over CS squared, which is an educated guess. But the reason you might think that there could be such a sum rule is that you already know, just from the lack of superluminal propagation, that this quantity should be positive. You shouldn't be allowed to have CS greater than 1. So the positivity of this quantity is kind of enforced by things you already know. And you also know that when CS is very small, you get large interactions. So that's also suggestive. But trying to actually prove such a relation just by direct attack has proven difficult. And one of the main difficulties is the lack of Lorentz invariance during inflation. OK, so rather than direct attack, I'm going to ask a seemingly totally unrelated question. And we're going to see that it finds there's some connection. So the question that we're going to ask is, what is the meaning of scale invariance during inflation? Is it indicative of some emergent and highly complicated phenomena like a fractal, or is it some boring fact that's relatively trivial? Well, lowest order derivatives in the sum rules, you extract the lowest order derivatives by some set of Cauchy argument, right? So it's not your goal is to learn what you can in principle, but in those examples, the lowest order derivative fixes everything with a higher derivative. So in principle, you could do a sum rule for a whole bunch of different derivatives, but the lowest derivative one is somewhat interesting. Which counterargument to which statement? So you can write effective theories where this is true. The question is, are those valid effective theories? So I can certainly write, so it's the same as putting constraints on P of, like, so for example, you could pick P of x to be whatever function you want, and you could ask, what is the space of PXs that are valid as a UV completion? Okay, so naively, scale invariance is a somewhat unremarkable statement. Scale invariance is a statement about approximate symmetry, and it seems to be related to a statement about another approximate symmetry, namely some symmetry of the potential. So it's unremarkable not in the sense that it's easy to write down a model that has a symmetry, but just that it seems to contain no particular different additional information beyond some statement of symmetry. Now this is in contrast to the situation with scale invariance in a unitary and relativistic quantum field theory. So in particular, it's proven in 2 dimensions, and I think largely proven in 4 dimensions, that if your theory has scale invariance, then it also has conformal invariance. And once you have conformal invariance, it leads to a bunch of unitarity bounds on the dimensions of operators, and the whole bootstrap program where you can construct more or less the entire theory with some limited input just from the fact that you know it's conformally invariant, and that follows from scale invariance. So adding this one symmetry dictates a lot of structure that you wouldn't have anticipated beforehand. Now, the purpose of this talk is that the scale invariance of inflation and the scale invariance in Q of t are related. In the context of DFCFT, this is obvious, but it's also not terribly useful because the CFT is not unitary and you don't know any of the rules. But ADS CFT, it's a very powerful statement because on the boundary of ADS, you have the full power of quantum field theory. And what we'll do in this talk is we'll show that you can take any model of inflation that you can map it to an effective theory that lives in ADS, and that effective theory in ADS is constrained by your full knowledge of the boundary. And so this is going to lead to this is going to be dual to some RG flow on this boundary Q of t that has some interesting properties that are fairly well constrained. And the question will be, what do we learn from the intersection of the constraints on the RG with our knowledge of inflationary model building, which will look something like this. We'll have information on the Q of t side, information on from this EFT in anti-de Sitter, and there'll be tension between these two things that will inform both directions.
So you're going to probably address this, but that upper right box is interesting in itself, but it's not directly the same.
Yes, so we'll then have the argument. Okay, we'll come to the end of how you then take the information here and try to get it back to there. Okay, so now about this map. Sorry, was there a question? Okay, so I'm first going to review some facts about the EFT of inflation, which most of this audience knows pretty well. But the reason that I'm going to go over them is because it's very closely related to this EFT for holographic RG. In particular, the EFT of inflation is spontaneous breaking of time translations. You introduce a variable u, which linearly realizes the time translations that are broken by adding in the Goldstone boson. And then you can write a general action in terms of u and derivatives of u, where you have these coefficient functions, which are whole functions of this variable u, which depends on t. The EFT of holographic RG is exactly the same, but you replace t with the radial direction in ADS z. You define a variable q, which is z plus pi. Again, pi is the Goldstone boson. You write the action for the Goldstone boson, which can have these coefficient functions that I've suggestively named m, the same variable here, and an expansion in derivatives in the same way. So this is, I'm foreshadowing here. I'm going to review inflation first, but keep in mind everything I say here is going to basically happen there as well. Okay, so as you all know, you can use Einstein's equations to solve for the first two coefficients in this theory. So m0, which is order 0 in pi to leading order, and m1, which is linear in pi to leading order, are fixed by Einstein's equations. In terms of the Hubble parameter of the background, enforcing that it's quasi-de Sitter demands that h dot is much less than h squared. Enforcing that the power spectrum is small, so the fluctuations during inflation are small, enforces that m Planck squared h dot is much greater than h to the fourth. The fact that these two inequalities are different directions is going to play an important role in the talk. And finally, we can get approximate time translation symmetry if we demand that basically all these coefficient functions are approximately time invariant. So instead of being whole functions, they're more or less constants. And this assumption here is related to having an approximate shift symmetry for the Goldstone boson. Finally, there's one more term that contributes to the quadratic action. This is the parameter m2, which changes the speed of propagation of the Goldstone boson. So you can rewrite m2 in terms of the speed of sound. And okay, this combination 1 minus cs over cs squared is not surprisingly the same thing that I wrote in my guess at a dispersion relation. Okay, so what's going to play, symmetries are playing an important role in this discussion. And so if we take the flats, we can take a flat space limit, or we can take the decoupling limit, so that we can think of this as a global, in terms of the, not a gauge symmetry, but just an ordinary space-time symmetry. So we're spontaneously breaking time translations. And so what that, and the generator of time translations is the stress tensor. So what it means that the symmetry is spontaneously broken is that when I act on the vacuum with the stress tensor, I produce a Goldstone boson. So there's a linear term in the stress tensor that's linear in the Goldstone boson, and the coefficient in front of that term is the decay constant for that Goldstone boson, which sets the scale of symmetry breaking. So here I've written it in terms of m Planck squared h dot and cs. And at the limit you take cs to 1, this becomes phi dot squared, which is exactly the scale you would have guessed is the scale at which time translations are broken. Boosts are also broken for the reason that you just construct the boost out of the original current. So if the stress tensor creates a Goldstone boson when acting on the vacuum, so does the boost operator, because all you did is multiply the boost operator, the translation operator by x. So you also have this linear term. But when you make this declaration that I'm going to take all of these coefficient functions to be nearly constant, there's this new symmetry, this shift symmetry of the Goldstone boson, which has a current J. And you can combine that with the original symmetry so that you make a new current that's not spontaneously broken. It's explicitly broken, but at a much smaller scale. And so this is where scale invariant, this is the current that is responsible for what the approximate time translations you see in the theory after making this assumption, and responsible for approximate scale invariance. And so this is the kind of hierarchy of scales you have generically. You have a symmetry breaking scale f pi, which is well above h squared. This ratio is what gives you the power spectrum. So h squared over, so normally this combination is, this ratio is something like 10 to the 4. And then you have this other scale h dot, which is well below h squared, where this approximate diagonal time translation emerges, and it's explicitly broken at this scale. So this ratio of scales, which is small, h dot much less than h squared, is what gives violation of scale invariance. But the boosts, which are going to be related to conformal invariance, are broken at a much higher scale. And so as a result, you find that correlators generically are scale but not conformally, approximately scale but not conformally invariant, with the exception of slow roll. So in the case of slow roll, you set all of the higher derivative interactions to 0, and then you can actually, you're allowed to have a higher spin current such that there's a diagonal boost symmetry. But this is really, because you have a free theory, you're allowed to do this. So the statement that you can have approximate conformal invariance is related to the fact that you don't have large interactions. Okay, so now we can repeat this whole story in ADS. For the purpose of, for right now, this can be ADS 5, so the boundary is d equals 4, where we can use our more favorite tricks about Q of t. And so again, it's the same story. I have this Q, I have z plus, which is equal to z plus pi. I solve for the first two m's in this expansion, and I demand a quasi-de Sitter background where I've described the ADS curvature in terms of parameter I'm suggestively calling h, where h is 1 over the curvature of ADS. And primes are derivatives with respect to the z direction as opposed to dots, which were previously time derivatives. But everything follows exactly the same. It's the same discussion. I have a sign flip here and a sign flip somewhere, a couple other signs, but it's exactly the same effective theory. So again, we're going to end up with approximately scale but not conformal invariant correlators as we approach the boundary. Another important fact, which is not totally obvious, is hidden in the fact, the way that I've labeled this variable z, is that the correlators have to be Lorentz invariant in 4 dimensions. Because those are what would have been translation invariance in inflation in just the spatial directions is now the full Lorentz. I have full Lorentz invariance on the boundary. So I now have, so that will give us access to tricks exploiting the fact, our knowledge of Lorentz invariant Q of t. we can go even further, which is to take the so-called decoupling limit, where we take m Planck to infinity and h prime to 0, holding fixed the pion decay constant. In this limit, the violation of scale invariance actually goes to 0, so you get exact scale invariant correlators. But again, conformal transformations are generically broken at the scale, so you're in this limit, you're approaching arbitrarily close to scale but not conformally invariant correlation functions. Okay, so as I've hinted, that's somewhat in contrast to what you've expected on the QFT side. So now the goal is to figure out how that meshes with our knowledge of QFT. Okay, so what's the dual to this statement? So the bulk is dual to some RG flow on the boundary. So you start with some CFT, but you deform it by some operator so it's a relevant operator, but you pick its dimension to be 4 minus epsilon, where epsilon is a small number. So naively, you think I made it a small number so I have control, but that's actually not really what's going on, because so what happens is now the trace of the stress tensor is non-zero because you've generated an RG flow, and the violation is proportional to the beta function. Again, as you would expect, I'm breaking scale invariance. The trace of the stress tensor is the measure of the breaking of scale invariance. But the beta function is related to just its epsilon times lambda. Lambda is the coupling, epsilon is a small number. But that ratio is given by what's the equivalent of f pi in this theory, f pi to the 5th over h to the 5th, which we said had to be much greater than 1 for control of the effective theory. So the beta function is very large. It's a number much bigger than 1. And since this isn't really model of inflation, I can pick this to be whatever I want. I can make beta squared arbitrarily large. Now, again, there's a diagonal scale invariance that's realized in the usual way. There's a new global symmetry. There was a global symmetry of the original CFT that's also broken by this deformation. So this global symmetry is broken, but by the exact operator that you would generate here in such a way that this combination is conserved. So there's a new scaling transformation that's realized by the original scaling symmetry plus this new current in such a way that d mu is approximately conserved. Now, again, we can take the analog of this decoupling limit. We take the coupling to infinity. We take the breaking of scale invariance to 0 such this combination is fixed. And in this limit, this current becomes exactly conserved. So I have exact scale invariance because I have the conserved current. But I still broke conformal transformations because I have a non-zero and actually very large trace of the stress tensor. So this is the point in which you should be concerned, is you should say, well, this sounds exactly like the idea that is supposed to be forbidden by field theory. The idea of combining the broken scale transformation with another symmetry is exactly the one loophole in the arguments against scale but not conformal that these groups were trying to kill. So what was their argument? So you start by assuming exact scale invariance. But you assume exact scale invariance of this form. You're assuming it's going to combine a global symmetry with the original, with some underlying scaling symmetry that's broken. And you add sources for the two generators. So you add a source for the stress tensor called g mu nu because it's related to the metric. And you add a source for this additional current c mu. And you demand that the generating function for correlations are invariant under this combination. So it's, again, some combination of both the original scaling symmetry and this global symmetry. And it's conserved up to potential anomaly terms, which are fully determined. And now you can take this thing and compute you can add the dilaton for what would have been the broken conformal invariance. So you've demanded the scale theory is scale invariant, but you haven't demanded conformal invariance. And so you say, well, I'll add the dilaton to realize the conformal invariance. And if the theory was already conformal invariant, the dilaton shouldn't have to do anything, and so it should be free. But if the theory is scale but not conformal, the dilaton has a role to play, and it should have non-trivial interactions with this theory. And so you compute this object, the 2-to-2 scattering, basically, which is computed as a 4-point function of the trace of the stress tensor. And you compute the forward amplitude for that object, for the dilaton scattering. But because it's scale invariant, that thing is completely fixed. This is the exact answer for the 2-to-2 dilaton scattering. And in particular, alpha is some constant that's purely real. But because unitarity relates the real and imaginary parts, and you've said there's no imaginary part, it actually fixes alpha to 0. So this is their argument that this is the argument that scale equals conformal, is that this dilaton was supposed to be realizing the full conformal group by doing something interesting, and in fact it has trivial scattering. It has a trivial cross-section with this scaling theory, so the original scale, the original scale but not conformal theory actually has to have full conformal invariance. So we're not quite doing that because our amplitude will schematically take this form. There's a parameter here, epsilon, which is proportional to the breaking of the symmetry. So there's nothing wrong with having terms that are non-analytic in S and can generate this sort of the branch cuts and things that you'll need in order to have non-trivial scattering. And if you have a scattering amplitude like this, again, there's nothing wrong if I fix lambda and take epsilon to 0, the breaking of my symmetry, the amplitudes will go to 0 as promised, and everything will work. But now if I take this different limit where I take epsilon to 0 while taking the coupling to infinity, now I can seemingly get all sorts of things. And it's not obviously in contradiction because the original argument, I started assuming epsilon was 0, and I proved various things. But the question is there anything wrong with this particular limit? But it's pretty close to being dangerous, and so the question is, can we get something from it? Yeah, it's like phi prime, the gradient of phi in the z direction. Yeah, so their argument would have been related to like the leading piece of this, which is formally infinite. So it said the formally infinite part in lambda goes to infinity is 0, which is true. And this is saying, well, they didn't say anything about the subleading parts. And we're just saying, because you take the coupling to infinity, you can have something finite that formally the 0 is 0 at any, if you fix any finite coupling. And it's just some statement that you can have exact scale invariance at leading order in 1 over n, but there could be higher, the 1 over n corrections will always break scale invariance by some amount. And the question is, yeah, so I think there's nothing formally wrong with this in that sense, but again, it's dangerous. This is a quantity that has been well studied, and the question is whether this is okay is not totally established, but I'll argue that it leads to what we were interested in the first place, which is a dispersion relation for the parameter M2. And so in particular, so this was the object that they were studying. They were adding the 2-to-2 total cross-section of 2 dilitons into anything in this scale but not conformal theory. And they have a relationship between the forward amplitude at 0 energy to the integral over that. But this object on the left is something we can compute in the bulk. So we have an effective theory in the bulk. And this amplitude in that limit is proportional to M2, M2 to the 5th, and that's it. It doesn't get contributions from higher powers of M2. And so you can write, this produces a dispersion relation purely for M2, which was this, which I'm not writing in terms of CS because this is an ADS. But it does tell you so it implies a positivity bound. This M2 to the 5th has to be greater than 0, which you could have derived similarly to the inflationary case just from basic causality. But it has this interesting property. If M2 to the 5th is equal to 0, the total cross-section is 0, and therefore all the higher m's are also 0. And so if I were to reinterpret this as a statement about inflation, it would say that CS equals 1 must be canonical slow roll. And of course, this is also interesting because CS is a parameter we can bound from data. OK, so kind of a summary of where we are. So inflationary model building has interesting connections to quantum field theory. So it appears there's nothing wrong with this statement, that you can get very arbitrarily close to scale, but not conformal correlation functions, which when I've asked people who've thought about this on the QFT side, was not intuitive that this was what would happen, but it's not obviously in contradiction. But now you can also start doing more things. So you add your favorite models of inflation, say monodromy. You have oscillations in the potential that are related to some sort of discrete scale invariance. That's related to some discrete scale invariant boundary theory. You can add disorder, some kind of disordered RG. You can do interesting things. And this is somewhat related to a literature on exotic holographic RG flows where people kind of write down crazy models in the bulk. But here there's more of a way to just get those models from things we've already done, which is take your favorite model of inflation and see what RG it corresponds to. But we've also seen the information can flow the opposite way. The QFT doesn't just accept every model of inflation as working, and it can reveal new constraints on the bulk EFT. Yes. We're going there. That's literally the next topic after I have one slide before we get there, but yes, that's the end of the talk. Okay, so now I want to extend beyond ADS5. But just to say that this isn't useless, what I'm saying though is any idea you had an inflation model built, like this part is just you take monodromy as an example. There's monodromy in ADS, like that model is perfectly valid, and that maps to discrete scale invariance, which was an interesting phenomenon in QFT that was, again, largely thought to be impossible in relativistic field theories. So it's not a totally innocuous fact, even though right now it's still just ADS. Okay, so now we want to extend beyond ADS5, so that both means lowering the dimension and hopefully switching to de Sitter. So to do general D in ADS, this argument we used specifically exploited attempts to prove scale but not conformal in 4 dimensions. But there are other related quantities that work in general dimension. In particular, there's a bound on the sign of anomalous dimensions for the lowest twist operator of spin S that has to always be negative. Anomalous dimensions on the boundary are again related to bulk interactions, and bounds on these quantities relate to a bunch of bounds on these M sub n's and sum rule. So these come from some kind of sum rule, and so this relates to some kind of sum rule for M sub n. And in particular, M2 appears to be related to the anomalous dimension for the spin 2 lowest twist operator. You can also try to prove this directly from causality of the 4-point function, which also seems to be, it's a related but different argument. And so, yeah. And so that's what, so in the pure ADS case, the argument of Adams et al. Is related to both these things. So you can prove the Adams et al. Sum rule on the boundary either by showing that if you had the wrong side, it produces the wrong sign for this anomalous dimension, or you can prove it by just directly going to the 4-point function and showing it generates a 4-point function that's inconsistent with causality. But okay, so the question that has now been asked twice and is on everyone's mind is then now you want to go to inflation itself. So the direct application to DS fails because the CFT is non-unitary. So you can't use unitarity to just rerun the same argument in using DS CFT. And so your hope is that this is that the first step would be to say this EFT has a flat space limit, and you think that whatever you're finding on the boundary should be representative of something you could have even proven in the flat space limit of this theory. So this is what happens in ADS. As I said, these facts that we're finding about the boundary theory are related to the Adams et al. Flat space argument about this effective theory. And so it should be some local constraint you can see, and this is just one way we're seeing it. And so there's, maybe said differently, it's not clear why this bound should be deeply tied to the global structure of ADS. It seems much more likely to be something you can see locally inside the horizon. And that's exactly what happens in these cases. So maybe to be more specific, you could try to run exactly the argument. You can take this flat space limit and look at forward scattering. And this is what the amplitude looks like. The amplitude takes this form, m2 to the 4th, and the Lorentz invariant combination s squared plus t squared plus u squared. But then the bulk theory breaks Lorentz invariant. So there's just like an s squared with some horrible function of all these 3 parameters. So you can put some bound on all of these parameters together, but it has this feel of not really capturing the physics correctly. So you get some bounds, and particularly you get a bound on the sign on M4 that's kind of interesting. But it's also clear, like there's also clearly some distinction between this term and this term. And in particular, the M2 term, the one that's proportional to CS, is the only one that has a D-wave component in the 2-to-2 scattering amplitude. So if you could isolate the partial waves and you could make a sum rule directly for the D-wave amplitude, you would isolate this term. So that's hard to do. sum rules that work in partial waves are not terribly useful. But what basically seems to be happening is that in the ADS example, as we take these correlators to the boundary, we have to recover full Lorentz invariance. So we basically had two options. This piece that doesn't look like Lorentz invariance either had to disappear or it had to grow a t squared plus u squared in order to capture the full Lorentz invariant structure. And what it seems to do is just drop out, and that's how we isolated this combination. And that's the same as the fact that we seem to be generating an anomalous dimension for the spin 2 operator, which again is capturing the angular dependence. So there's some hope that you could just directly prove this in the bulk, but it's because of the lack of Lorentz invariance, it sort of doesn't. It's hard to use the existing tools. So tools beyond what we know would have to come into play. Okay, so just to wrap up, so what I've presented here is that there's a map between any ideal you have in inflation and some RG flow of a Lorentz invariant and unitary quantum field theory. Sort of things that we've liked to think about in inflation for a long time seem to map to particularly interesting and exotic RG flows in this way. These quantum field theories have constraints that come from the fact we know a lot about them, and this seems to map to interesting new constraints on EFTs that live in the bulk of ADS, including constraints on the signs of couplings and new sum rules. And this suggests that there should be some way, perhaps, to derive these sum rules directly in the bulk in a way that would then presumably also map back to inflationary parameters. Okay, thank you.